Hi, I'm Canchen, and in this lecture we'll be talking about ownership in Rust. So we'll be covering ownership, and as additional reading, you can look at the Rust book chapter 4.1, which should cover similar content as this lecture. So let's give a brief introduction as to what is ownership, and it is one of Rust's most unique features, and it basically is a set of rules for how a Rust program manages memory. And what makes it unique is that its ownership model is very different from how many other programming languages manage their memory, right? So before we talk about the ownership system, let's talk about how does memory look like in a program, right? So you might be familiar that there's like stack memory and heap memory, and these are two different places where you can store variables when you run a program, right? So in a typical C program, right, the memory layout usually looks something like this, right? Where here we have basically like the memory used to store like the actual instructions that need to get executed by the computer. So this is like the code, right? And then you need some space to store your variables. So you would have like the stack, which grows down, and the heap, which grows up, right? And they grow in opposite directions, blah, blah, blah. But basically, you can think of, right, there's like some space on the stack to store variables, and then some space on the heap, right? Okay, so let's talk about some differences between the stack and the heap. So with the stack, you don't need to manually allocate space for each variable. You can just say, okay, I want this variable, and the compiler should know this variable will take this much space, and it will be able to automatically give it some space on the stack, right? It's fast to access values on the stack because we know exactly where they are. We don't need to like do any pointer chasing. So the stack has limited size, but we mean that as in like the compiler needs to know how much space to give that it needs to reserve on the stack beforehand. So we can only use it to store things that are of a fixed size, right, as it says. So for example, if we want to store one integer, we know that the integer ahead of time is going to be 4 bytes, right? So the compiler can say, let's reserve 4 bytes of space on the stack. So the difference with the heap is that you need to manually allocate space, and it can be a little slow because once you manually allocate the space, right, you get a pointer to like the space that you just got. So now if you want to like access the value, you have to like chase the pointer. And the difference is that the heap can be expanded, so we can use it for data of unknown size. So for example, if we like read some user input, let's say it's like somebody's name, right? People have different lengths for their name. You know, some people have longer names, some people have shorter names, whatever. But like by using the heap, we can dynamically allocate the right amount of space for this user input, right? Because we don't know how long the string the user is going to type in is beforehand. So that's a little bit about the stack and the heap, right? So an analogy for the heap that we've been using is that the heap is like a restaurant. So for example, when you go to a restaurant, you tell like the host, the server, how many people are in your group, and they'll find a table for you that fits that many people, right? So similarly, when you use the heap, you have to ask for memory on the heap, and you tell the computer like, okay, I want this much memory, and the computer will find some space and hand you a pointer that tells you, okay, there's the memory you got, right? The other difference is the other similarity is that at a restaurant, the amount of customers that will come in is not known by the restaurant ahead of time, right? It's like kind of arbitrary, like what groups are coming into the restaurant, and the restaurant just has to like accommodate for them. Similarly, right, the amount of heap memory you need for the program isn't known by the compiler ahead of time, right? For example, back to the user input example, right? We don't know how long the name that the user enters is going to be, so like the computer has to be flexible with how much memory it allocates on the heap, right? Okay. So we can talk a little bit about memory management. So what do we need to do in order to use heap memory successfully, right? One, we need to ask the heap for some blocks of memory. We need to keep track of which memories we're using. And then after we're done using it, we need to give it back to the computer, right? So that maybe other processes can use it, or we can use it to store other variables in the future. So some approaches to memory management. This first approach is manually managing the memory. So for example, you do this in C and C++. So you'll ask for some memory space, and you'll have to manually return it when you're done. So in C++, this is done with you use the keywords new and delete, right? So new will allocate some space on the heap, delete will free that space, and then maybe in C you use like malloc and free, right? So what are some issues with this approach, right? It's that, well, you're manually managing the memory. So if you free if you free the memory too early, right, and you try and use that freed memory later on, your variable is invalid because you just said, okay, you handed the memory back to the computer. It's now free to do whatever else it wants with it, right? So the data that's there might be garbage, right? If you don't free it in time, you're just keeping around this like useless space that you've allocated, right? You're not using it for anything, so you're kind of just like wasting space. And then if you accidentally free like the same pointer twice, you end up with undefined behavior, right? Because you've already given this back to the computer, right? So it's undefined as to what it does. The other approach that's commonly used is through garbage collection. So for example, in a language like Java, where a special process runs alongside the program that will automatically return memory that you're not using anymore, right? So while as your program is running, this garbage collector is looking at your program and looking at, okay, you've allocated this memory, but you aren't using it anymore, so I will take it back, right? So what's bad about this is that, one, you need this extra process to be running on the side that's constantly looking at the memory, right? And this will affect the performance of your code. So let's talk about what Rust does. Instead of this manual memory management or this garbage collection approach, Rust uses ownership, right? And some advantages are that ownership is fast because it doesn't use an extra process like garbage collection does, right? For example, we might not know exactly what the garbage collector is doing, but we can have a pretty good understanding about the ownership system ahead of time. And then there's also no manual memory management needed from the programmer's side, right? The compiler will automatically use the ownership system to decide when to free data. So let's go over these ownership rules, and then we'll look at how these are applied in practice. So the rules are each value in Rust has an owner. So every value is owned by somebody, right? They can only be one owner at a time. So each value can only be owned by one owner. And then when the owner goes out of scope, the value will be dropped. So this tells us when we are able to free memory. So we'll give a quick demo about variable scope as a brief recap, right? So for example, here's some code. And variable scope is defined as the region in which a variable is valid. And it's usually denoted by these braces. So for example, here we have a set of braces. We declare S inside the set of braces, and then S is only valid inside these braces, right? This is the scope of S. So for example, if we try and use S like before it's declared, of course, clearly that's not going to work. But if we try and use it outside these braces, like for example, if we want to print line S, we need to wrap it in some quotes. We'll see that it'll actually complain if we run cargo check that S is not found in the scope, right? Because the scope of S is precisely within these braces. So if we connect this back to what we said about the ownership rules, right? Once S goes out of scope, the value it has is dropped, right? So let's talk about some data that lives on the heap, and that is through this string data type. If you'll remember, we have these string literals versus like the string class. So here, this S here is a string literal, and the data here, well, it doesn't live on the stack. It lives in like some static memory area, and then S is secretly a pointer to that static memory area. But basically, it doesn't live on the heap. Okay. So for example, here S is a string from hello, so it'll create a new string that contains the like characters hello, right? And this is basically hello gets put on the heap, so these characters are stored on the heap. So here's a different example where empty starts off as an empty string, right? We create a new string, and then we're able to push string something, so this will put something on the heap, like these characters will be stored on the heap. And the reason we're allowed to do this is because like we can ask the heap for more memory, right? So even though this string is empty and it doesn't take any memory on the heap at all, when we push string, we can always ask for like more heap memory to put these new characters on the heap. So if we go back to the idea about scope, right, the region in which an item is valid, when a value on the heap goes out of scope, the drop function is called to free the memory. So for example, here we create a new string s from hello. So here we put these characters hello on the heap, right? And then once s goes out of scope, outside the braces, this variable is dropped. And what happens is that the characters hello that we put on the heap are freed, and the memory can like go back to the computer and be used for other things. And note that this process of calling drop happens automatically, right? We don't need to manually specify that, okay, we allocated this memory and now we need to free it. It happens automatically because of the ownership rules and the scope, right? Of course, we can actually manually call drop on like variables to free them manually, but it's not good practice. So we can compare drop versus garbage collection, right? The difference between these two is that drop happens during compile time. So the compiler inserts instructions to do the drop. And this is because the compiler can look at our code, analyze, okay, here's the scope for the variable s. We know that s goes out of scope here, so we can just insert the drop command, like drop s, right here at the end of this, right? But when using garbage collection, this happens at runtime. So as we're running our code, blah, 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 stuff happens. Suddenly we detect s isn't being used anymore, and then like this data hello will be freed. So that's the difference between Rust's ownership system and drop versus garbage collection. Okay, now let's talk about why are we some more reasons and why we're interested in using ownership, right? So in this example, we set x equals to 5 and then y equals to x, and in this case these are both integers and they are allocated on the stack, right? So when we assign y equal to x, we can just copy the memory for x and duplicate it for y. So x will contain some bits like 101 and then y contains the same bits. So now let's consider this new example where it's similar but we're using strings instead, right? So the way we can think about the representation of the string in memory is that there's some portion of S1 that is on the stack, right? So it'll store some information about it, like a pointer to where the data is allocated on the heap, and then maybe like the length of the data and like how many it can hold. So it says, okay, we have 5 characters on the heap, and here's a pointer to them, right? This is stored on the heap. Now, let's consider what happens when we assign S2 equals S1, right? Does it look like this, where we've essentially like created a deep copy of everything, right? S1 is pointing to its own copy of stuff on the heap, and S2 is also pointing to its own copy of stuff on the heap, right? Is this what's happening? Actually, no, because it's pretty expensive to do a deep copy every time we do some kind of like assignment like this, right? So what might happen in other languages is that when we have something on the heap and we do this assignment, we secretly just have both of them point to the same item on the heap, right? And to prove to you that this is something that happens in other languages, we can look at this example of Python code for fun, right? Here we have a list, we do this assignment, and then we'll modify only S1. But if we run this Python code, let's see. Oops. We'll see that actually S2 gets modified as well, right? And the reason for this is that both S1 and S2 are pointing to the same data, right? So that seems a little weird and unintuitive. But there's a different problem here, is that what happens when S1 and S2 both go out of scope, right? So Rust will automatically call drop for you. So what ends up happening in this model is that if once S1 gets dropped, this heap data gets freed, and then S2 gets dropped and it gets freed again, and we have a double free error, right? So this doesn't work. So what really happens here is that when we do this assignment, we have to invalidate S1 and say, okay, like whatever data S1 is pointing at, we don't care anymore because we've moved it into S2. S2 is now going to take ownership of the data that was pointed at by S1. Right? So this maintains this model. Each value in Rust has an owner. So here this value is going to be this string hello on the heap. There can only be one owner at a time. So when we assign S2 to S1, S1 to S2, right, we have to say S1 needs to give up its ownership and give it to S2. And then when the owner is out of scope, the value will be dropped. So now here, S2 is the one owning this data. Once S2 goes out of scope, the value will be dropped. This means that S1 is no longer valid, right? So if we think back some time ago, what if we did want to do a deep copy, right? We can explicitly do a deep copy by using the clone function. So yeah, that's pretty much it. And now we'll go over a small demo of how these ownership rules with more examples. Okay, so let's look at this example. Here we create a new string s, right? And we call this function takes ownership. So takes ownership, we pass it this string. So some string comes into scope here. We do something with it, and then once we hit this brace, some string goes out of scope, right? And it gets dropped. So here what happens is we have s. S is, when we call takes ownership, s is moved into some string and then it is dropped. So the value associated with s is now gone. So if we try and use it after this takes ownership function, for example, if we try and print out s, we should get a complaint, right? And what happens? Let's ask it to cargo check. And we see, okay, we've borrow of moved value. So we've moved the value and we're trying to use it, but we can't, right? So it suggests that the solution is we can use s.clone. So instead of handing ownership of s over to this function, we can create a new copy of s and hand it to the function instead, right? And now everything is happy. So in this example, this takes ownership function will take ownership out of whichever variable is passed into it. Okay. Now let's look at the second example, this makes copy function, right? This is the same code as above, but with an integer x instead, right? But here, the compiler doesn't complain when we try and use x after we call this makes copy function, even though it looks like it's doing the same thing as takes ownership, right? What is happening here? The difference is that x is of type i32 and it implements this copy trait, which means that instead of passing in the value directly, it secretly here makes a copy and then gives it to the function instead. And the reason we can use it does this is because there is no data on the heap that x is storing, right? Since x is just an integer and all of its data lives on the stack, it's safe to make a copy, and the compiler automatically does this because x implements the copy trait. So that's a little confusing and something to watch out for. I also got some more examples. Here we have a function gives ownership, which returns a string, right? So here we create a new string, some string, and then we return it, right? This is using the implicit returning where the last statement without a semicolon in the function is its return value. And here we assign s1 to gives ownership, right? So gives ownership runs, some string is created, and it gets returned and passed back to the main function. So here we have ownership over s1, and we can do stuff with it, we can print it out, right? So this is good code. We're missing an underscore. Right, so this is perfectly valid. And then once we hit the end of this brace, s1 goes out of scope, and this value hello is going to be dropped. Okay. Now let's look at the second the function, takes and gives back, right? So here we pass in some string, and then we just return it back. So we give it a string, and this function returns a string. Let's look at what happens here. First, we create a new string s2, and then we pass it to this function, takes and gives back. So this function takes ownership of s2, and then immediately returns this value back. So now s3 is now owning the value contained inside s2. So you can think about it as s2 transfers ownership to some string, right? And this function returns some string, and then the ownership is transferred to s3. So let's see what we can do here. If we try and print out s3, this is totally valid, right? Because we own s3 at this point. But if we try and use s2, it'll complain because we've already given s2 to this takes and gives back function, right? We've lost ownership of s2, and it returned a string, and we've set it to s3 instead, right? So now we only have ownership over s3. So here when S3 goes out of scope, this value will be dropped. Hopefully these examples helped you a little bit with understanding a little more about how this ownership system works. It's a little confusing because it's one of the unique features to Rust, right? But that was all the content for this lecture. We can review the ownership rules that we covered, right? Again, each value in Rust has an owner. There can only be one owner of each value at a time. And then when the owner goes out of scope, the value will be dropped, right? I feel like this has been repeated a lot throughout this lecture, but this is the most important rules when it comes to ownership and defines how ownership works. So yeah. As for announcements, homework 3 is released today on Prairie Learn, and it'll be due a week from now on February 24th. So thank you guys for listening, and hopefully this lecture was useful.